Third version of TPU, more powerful, more heat, more cooling. It is substantially more powerful, and we'll talk about each of these versions and kind of the ins and outs of it. Okay, so the first version of the TPU ran a 28 nanometer process, and that's since come down, and it put out 40 watts. So you can imagine, by the time you get to the third version, it came out considerably more. And it's been in use since 2015, search, translate, as well as Google Photos. How many of you guys use Google Photos? Yeah. Love Google Photos, it's great. And all of that image processing, facial recognition for all those pictures that everyone is taking, that's coming from TPUs since 2015. And in terms of performance of that first version of the TPU, the benchmarking basically led them to conclude that it was 30x per watt standpoint. Getting high throughput at low energy cost was 80x faster. And this was just the first version of the tensor processing unit. So it was really quite remarkable. And so that's kind of what made it so successful in terms of its use case. But why was it so good in terms of what underlying aspects allowed it to do this, right? So let's talk a little bit about how the TPU is structured at the chip level. So the first thing they did was use reduced precision. Now you might say, well, that seems like a bit of a hack and a bit of a cheat, but also, like, wouldn't that make things worse? And it turns out that when you look at neural networks, it's a bunch of multiplication and addition operations. And in particular, when you write it all out, it ends up being a matrix multiplication. You can simplify this down, this expression here, to be one matrix multiply. And so you need a chip that can do that at scale, right? And when you're doing these matrix multiplies, all of these floating point numbers have limited precision, and you have to carry all those bits around. But thankfully, because of the way neural networks work, it allows for kind of fuzzy math. And so the first and arguably the biggest kind of trick in terms of in their software tool belt was quantization. Turning floating point numbers into 8-bit integer representations. So that allows us to do these computations much more quickly, right? Integer computations are a lot easier than floating point numbers. And so when quantized, and that means you can make TPUs internally have integer multipliers rather than floating point unit pieces. So in, for example, a Tesla K80, which is a graphics card from NVIDIA designed for machine learning, it has about 2,500 32-bit floating point multipliers, whereas the TPU has its 256 by 256, so 65,000 8-bit integer multipliers. Even though the TPU uses 8-bit integers, the precision is not lost all that much, which is really nice. So how does it actually work, right? How is it able to process things so quickly in this specialized manner? So to understand that, we need to review briefly CPUs and GPUs, how they work. CPUs primarily rely on this notion of generalized processing and a reduced instruction set RISC language. And so what that means is a CPU will take an operation, right? It'll take a piece of information, it will do some simple operation on it, and then store it somewhere. And then the next thing will be, okay, now let's read it back from there, do something, and store the result somewhere. So it's a lot of intermediate storage and compute, and it happens in a somewhat serial manner. And that's why you have multi-threading and stuff like that, so that they can do it sort of in parallel. GPUs do this, a similar idea, but in a stream processing manner. So that's why you see all these colorful boxes. Each of those are individual cores, which can allow you to process lots of data at the same time. So this compute and write, read, compute, write, read, compute, write loop is kind of the Achilles heel, it turns out, of CPUs and GPUs. To allow for general processing, they have to design it this way. But this comes at a cost. right? This flexibility comes at a performance and energy, heat cost. Whereas if you were able to build a special purpose processor, one that could just do your giant matrix multiply in one operation with no memory writes, you could just pass it in within the chip itself, never going off the chip. And when it's done, then ship it. It allows you to have better memory, heat management, performance, and throughput. So you can hardwire these operators. What that looks like in process is this notion of a systolic array. Now, I know we're at a tech conference here, but for those of you who are familiar with human physiology and the heartbeat, you might know about the systolic and diastolic aspects of the heartbeat. So the reason why it's called a systolic array is because the inputs come in waves, much like the systolic, much like systole of the heartbeat, the lub-dub. So this is what it would look like if we had a vector coming in. And in the case of a matrix, you kind of do that offsetting, and then you push it through kind of like this wave of data. And that results in this output. We'll let the animation finish. And one more. Okay. So that's how it's able to do kind of a larger matrix multiply at once. And another way to think about it, another analogy for this would be to say that in the CPU, a scalar computation, it's like printing individual blocks. Up in the upper left there, you see putting one block letter at a time. When we're doing it in one row at a time, that's kind of like GPUs, stream processing. You're pumping out an entire row of values at a time, printing them out. Whereas with the TPU, it's like printing an entire page at a time, right? Like the Gutenberg printing press. Boom, a page. Boom, a page. So this is what the block diagram for the TPU version 1 ended up looking like. Pay no attention to the image on the left. The notable thing is that with the matrix multiply array of 256 by 256, you end up with 65,000 8-bit multiplies. It's running at 700 megahertz. So it works out to be slightly blank on the number. I think it's something on the order of 90 trillion operations per second. It's absurd. So yeah, if you take 65,000, multiply it by 700 million, right, 700 megahertz, you get a big number. And so that's kind of the crux of it, right? The CPU can do a few operations per clock cycle, admittedly at a faster clock cycle rate. A GPU can do thousands of operations per cycle because it has lots of individual cores, thousands of cores. But a TPU ends up with hundreds of thousands of operations per cycle because it's kind of kadunk, churning through all this data in one shot. Of course, with that comes inflexibility in the programming model. A TPU is not going to be useful if you want to run your Chrome browser on it, for example, right? It's only good at doing matrix multiplies, nothing more, nothing less. So it's really designed for doing machine learning, working with neural networks. And from working for the standpoint in terms of software, the team built a number of dedicated compilers and various tools to allow developers such as yourselves to still be able to code it from a kind of high-level standpoint, which is really great. The performance per watt of the first generation TPU was 83 times better than a CPU, which is crazy. And this is, just to be clear, a log scale that we're looking at. So let's dig a little bit deeper into the design of the chip than we already have, right? So another part of what allows the TPU to be so performant is that only a tiny amount of the board, that red portion there, is dedicated to control. Things like multiprocessing, context switching, caching, all that stuff is out. I don't need it. All the things that help a CPU be a great even, general purpose processor is what holds it back from being a great specialized machine learning chip. And so a TPU does away with all that, replaces it with these massive matrix multiply units, and interestingly enough, the area of the chip actually ended up being quite small. It was actually half the size of most CPUs of that time. And because of the way silicon is printed and wafer sizes and yield rates, the cost of the chip ends up being 2 to the third less, 8 times less by having the footprint of the chip, which is kind of an interesting piece of trivia. And moreover, they got guaranteed latency. They're designed for high throughput, 7 milliseconds in to out. And so this is kind of a throughput comparison. On the left, we see the TPU pumping out 225,000 predictions per second, all those Google Photos and Google Search results for you. And on the right side, we have 6 kind of representative models that were used throughout the company. They surveyed the company, and that's scaled relative to CPUs. So you see 1 for the blue bar. So CPUs are always 1, and again, that's a logarithmic scale. So at the extreme end, at the bottom there, you see CNN 0 and CNN 1. Those are image-based or image processing neural nets, convolutional neural networks, and TPUs outperform CPUs 40, or in the bottom case, 71 times faster, more throughput. So that brings us to TPU version 2, because TPU version 1 did really well, right? I think we can all agree that 71 times better than previous state-of-the-art. It's pretty good. So TPU version 2, they decided to take a picture of it with colored cables. I don't know why. But its main purpose was to improve upon the old design and build in training. This one comes with a pretty serious heatsink and lives in a dedicated kind of pod or box, and pumps out one of these 4-chip cards, pumps out 180 teraflops. Okay, so keep that number in mind as we go forward and talk about the other kind of numbers and performance. So the layout of the processor is similar, but with some improvements. They took the matrix multiply unit that we're familiar with, added 8 gigabytes of high bandwidth memory. This is, if you're familiar with hardware and kind of memory chips in the consumer side, you might hear of like DDR RAM, DDR3 or DDR4 RAM. So HBM, high bandwidth memory, is a spec that was built kind of, that goes beyond that. It's something that lives closer to the chip and has higher kind of exchange rate. So in the core, right, there's 4 of these on each TPU V2. There's 2 cores on each processor, and the matrix multiplying unit, now we've moved away from integer processing to what's called a B-float 16. So what is a B-float 16? I think this is even more clever than the quantization that we saw earlier. The B stands for brain, because it came from Google Brain. And a little review of floating point numbers, or maybe first time for some people. So a floating point 32 single precision number. So we see across that row, those are 32 boxes, okay? The first, well, there's the S, and then there's the 8 exponent bits. That defines how big the number is, right? So think scientific notation. We're going to use 8 bits to define the range, positive or negative. So the S is for sign, positive, negative, and then the exponent defines how big the value can get, or how small it can get, right? Because negative exponents. And then the rest are all effectively significant digits, sig figs. A floating point 16-bit number, right, standard IEEE, is only 5 bits of exponent and 10 bits of significant figures, the decimal, right, this point, blah, 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 blah. And you can see the range is much smaller. So whereas the range of a 32-bit floating point number goes from negative to positive 38 powers of 10, right? So it's a lot. The range for a 16-bit floating point number only goes from negative 8 to positive 8 power of 10, 10 to the negative 8 up to 10 to the positive 8. So what is a B float 16? It takes the same amount of space as a floating point 16-bit number, but it supports the same range as a 32-bit floating point number. Notice that the exponent bits are still 8. So the range is the same as when we had 32 bits, albeit we've lost quite a bit of the sig figs, right? We've basically dropped a bunch of decimals and just zeroed them out. The convenient thing about this, though, is that it allows you to do, firstly, comparisons between B float 16s and floating point 32s very easily, because the range is the same. You don't have any risk of hitting not a number and out of range errors, because it has the same range. So it's really just a reduction in precision. And in that sense, it's very similar to the quantization that we saw with the conversion to 8-bit integers, except here we're still preserving a floating point number. Okay, so all of that boils down to a lower cost, right? Running TPUs is both faster, but ends up being cheaper per watt than I guess GPUs or anything that came before it. So this is an example of running one TPU against for 10 hours, right? That's 65 bucks. I usually don't do too much with pricing here, so this is like my one pricing slide as a point of interest. There's a couple of different benchmarks out there today that have kind of come out in the past, call it 6 months. One is Dawn Bench. It comes from Stanford, and currently the cloud TPU on using AmoebaNetD has the lowest training cost in terms of money on Dawn Bench. So it hits the 93% final accuracy. So just like state-of-the-art accuracy, just like everyone is expecting these days. Standards are so high. And the training cost, less than 50 bucks to train a state-of-the-art model in, less than a workday, 7.5 hours. Let's take a look at another example. This is running ResNet 50 on the TPU Version 2, and it trains for a little more than a workday, and running at 3,000 images per second of training costs 59 bucks. And the folks over at FastAI did some interesting optimizations to the way they did the training in terms of feeding the data. And if you apply that same optimization here, the training cost gets cut in half. I have some quotes from customers because it's interesting to see how other folks are using it, especially when it comes to what in my mind is the primary application of TPUs initially, especially because they're so well optimized and suited for images, right? They have these big matrices to push the images through, and you need to push a lot of them. So self-driving cars seem like a really obvious application, but there are of course many others. Okay, so that was the first point. It was like the big thing. Okay, so now let's talk about the TPU pod and then how to program it in kind of two briefer notes. So a large-scale TPU cluster, taking one of those TPU V2 chips and giving you a supercomputer out of it instead of just one, very powerful computer. NVIDIA has the DGX2. It is 16 V100s. Okay, so if you're familiar with NVIDIA's machine learning lineup, right, there's the K80s, there's the Pascal cards, the P4, the P100, and then more recently you have the V100. That's like their top-of-the-line thing. And they stick it all into one giant box, ask you for $400,000, and hand you 2 petaflops of compute power. Great. A pod of TPU V4s is 64 of those chips, those TPUs, and pumps out 11.6 petaflops. So I guess if you want to compare apples to apples, not apples to apples, but when I was looking at this, I was like, well, earlier, it's not really fair because the DGX2 had 16 V100s and got 2 petaflops. Here we have 64 TPUs and we're getting 11 petaflops. So I guess, the scaling is a little superlinear, which is kind of funny. Okay, so one pod is 64 TPUs, but that's useless if the TPUs can't talk to each other, right? They need to work as one. In classical, not classical, but in previous machine learning distributed training algorithms, it utilized what are called parameter servers. All the values that a model is trying to train, trying to fine-tune, that is shared between all these machines, there are dedicated machines called parameter servers whose sole job is to relay information from this worker to that worker. Oh, this worker got a new value. Let me tell everybody else. So just broadcasting. That alone, and it's done over TCP/IP. It's done over the network. So not super fast, right? Well, if you put all the TPUs in one pod, into one physical place, you can connect it with a much faster network, and using it becomes the same as using a single node, a single machine. So it becomes similar to accessing a supercomputer, but this supercomputer is all TPUs. And so it scales linearly. It's just straight up. I put a dot there for where 16 devices would sit, right? If perfect scaling for 16 devices would be there, in order to get to 64 devices, you would need 4 of them, and what would you connect them with? A LAN cable or perhaps a USB 3, right? So this is just incredible in terms of just like the number of machines in one super connected, I want to call it a box, but it's really big, so we'll call it a pod. So one TPU pod. So for a pod, remember those training times we saw earlier for a ResNet 50? Does anyone remember what it was? It was like a little over 8 hours, right? We had one that was under 8 hours, one that was over 8 hours. So for a half pod, it's only 32 TPUs. Same training performance, more data throughput, 30 minutes to train a state-of-the-art model that previously, on a TPU, no less, took all day. A couple other kind of back-of-the-envelope examples. RankBrain, which was one of the older algorithms to do, that runs Google search. 132 hours on 275 CPUs. Scaling problems there, right? You take 16 TPUs, that's even less than what we just saw, 9 hours, done. One of our image classification models, 10x faster on, again, a quarter pod, 16 TPUs. And with a V2 pod, they were generating speech at 20x real time. I know I'm speaking you to now, so I don't want to like, I was going to try to like say like, oh, it's so fast, and try to say it, but I can't do 20x real time. It's too fast. You know, when you hit play on the YouTube and you're like, play at 1.5x, play at 2x, it's like, well, imagine if there was a 20x, it'd be like the video is like, oops, done. Another thing that having a pod enables is larger batch training. So in machine learning, let's say we have 1,000 images that we want to train, right? Typically, we don't push all 1,000 images into the model all at once. We put them in batches. We'll randomly select, we'll shuffle it up, and we'll pull from the deck, we'll randomly select, say, 32 images and show it to the model, and the model will adjust. And we'll pull another 32 images and show it to the model, and the model will adjust. And this will happen until the deck is empty. Then we'll take the discard pile, bring it back to the deck, shuffle it up, and do it again, right? It turns out machine learning is really just the card game. And so now, what if we could train bigger batches? We could put in more of the data. Then we can read through, say we want to kind of shuffle and deal 90 times, because we don't have 1,000 images. So we want to let the machine learning model see the data a little more for a little longer. So one full kind of deal to the bottom and then bring it back and shuffle again, that's one epoch, one pass through the entire data set. The bigger your batch, the faster you can get through an epoch, right? Assuming you can process that batch faster. And so with a TPU pod, in this case, half pod, you can go up to 8,000 images per batch. Right, so that gives you a sense of the scale. I mean, there are data sets that don't even have 8,000 images. So this is reading 8,000 images in a batch, and we're doing hundreds of millions of processes per second, right? And so that's that really fast curve that shoots straight up on the far left there. It hits the same accuracy, but in no time at all. All these curves represent the TPU pod processing the same amount of data, 90 epochs, 90 passes through this massive deck of images. But the first one, it's reading 8,000 images at a time instead of just drawing one card off the top. So that brings us to TPU v3. Not much to say here. Not much has been announced about it, unfortunately. As you might imagine, it is also organized into a pod, except this pod has 100 petaflops. It's 8 times faster than the TPU v2. So the scale of things is just staggering, right? I never thought we'd be even at the petaflop range, much less, whatever comes after petaflop. This is 0.1 of that. Okay, so that's the TPU pod, letting you take a chip and turn it into a supercomputer. So how do we actually use it? How do we program for a tensor processing unit? Which really, to be fair, now we should really call it a TPU pod, right? We're not really programming one chip anymore. We're talking about much more. The documentation is really handy in this particular case because it does take kind of a specialized approach, and it's pretty comprehensive in that sense and talks a lot about more of the nuances than what we've even talked about today. So TensorFlow has an API, the estimator class. The best news I've got for you is that distributed training, multiple GPUs, and TPUs are all built into estimators. So the amount of code changes you have to make is minimal. You have a TPU estimator, and you take your original estimator, and you add two things. And then you say, I'm done. Right? You take the TPU optimizer and you use this, what's called the cross-shard optimizer to wrap whatever optimizer you chose. And then you pass it up. Okay. One final thing. Earlier we talked about how TensorFlow, the Python is not obviously running on a TPU, right? We're not running Python to do matrix multiplication here. So there's a lot of stuff going on in between. There's a number of XLA, which is the accelerated linear algebra. It's a just-in-time compiler, and a number of other services in between, but you don't have to be too worried about that. It's just kind of a FYI. Those are there. You're not literally writing to the metal. And in practice, you run your TensorFlow code. The Tensor TPU is kind of hooked up to a host CPU, a VM, and you put your code there, and then it outputs stuff to the model directory. Data is coming in, and what's notable here is that the high bandwidth memory that we were talking about earlier, that was 8 gigs per chip, so there's 4 of those. There's 8 of those, actually 2 per core, and it's coming in and using that as a queue. Because the TPU is so fast, one of the legitimate problems that we see right now is we can't feed it data fast enough. It's just like, oh, I'm done. Got more? I need more. And so you got to actually think about this stuff now because the chip is too fast. And that's why there's these high bandwidth memories being used as a queue. Okay, so some general guidelines around cloud TPUs, when it might be useful, when it might be less useful. Generally speaking, you got to have a lot of matrix operations. Today, that largely means deep neural nets, convolutional neural nets, but that may change. And you want to have a lot of data. You want to have a reasonably big model with a pretty big batch size. You just got to just shove lots of data into it. And on the other hand, don't use TPUs when you have small data. If it's really sparse, or you need something that's super high precision, right? Because we've cut that precision down because we're using that B-float 16. And so basically the TPU, you can think of it as a highly tuned race car. It will drive down that straight smooth road just as fast as you can say go. But for basically winding roads where it's like, oh, do a little thing here, and then we're going to go over here, and then we're going to go to a scenic bypass, it's going to drive off the side of the road, so you don't want that. The final resource I want to point you all to is that there's a number of reference models already available. These are models that come with code, come with trained models. You can take them, they will work. You can apply it to your own data. You can fine-tune them. So this is really quite good, and the list is expanding. So this list used to be literally one model, and that was not even 3 months ago. So a lot has changed, a lot will change, but generally it's up and to the right. And let's see, I think that covers all 3 of our bullets. I have a flashing red light in front of me. So thank you so much. And I think, so I'm Yufeng. You can hit me up on Twitter. I'll post the slides there. g.co/cloudtpu links you to the Cloud TPU docs. And there were a couple of things I was supposed to say at the end. The Robot Derby is upstairs. I really wanted to do that today, but something about speaking and scheduling made that impossible. And there's a happy hour after the Robot Derby, during the Robot Derby, so you can have food and watch robots fight over colored balls Who doesn't want to do that? And I think Cheetah probably has a few things that he'd like to say, so I'll turn it over. Thank you all so much.